Okay, so good afternoon, everybody. So our today's goal is to prove Kiefer's theorem and to show how.
But it's not.
Yeah, I don't. So we are just at the second section.
Better miss the third part of your plan stuff and to understand that.
This is the goal for the moment. But before doing that, I will recall what we did yesterday. So we had a compact metric space.
Более шино проводить сделаем.
Да,
Окей.
and we have to open today. We'll assume that it is the space of probability measures. When this X is another compact space. Another, no, just a matrix, compact matrix space. We discussed it yesterday that if we consider the big star topology of dx, then this will be a compact matrix space, which can be metrized. This topology can be metrized. For instance, if we choose dense sequence, in the unit ball, and I don't specify the center thing that it's center of 0 in the unit ball of dx. But this is in case of continuous functions on x.
People use it before Prokhorov, Armen, right? Because Prokhorov distance, it is also metric, right? And Prokhorov distance was.
Yeah, Prokhorov distance works in any Polish space.
Excuse me.
It works on any Polish space, right?
Prokhorov is much more involved.
Yeah.
So this is before Prokhorov.
Definitely, yes. At least in simple cases, yes. Yeah. So continuous functions. Then you can metrize the big topology by the following distance. Distance between two measures is the sum j from 1 to infinity, 2 to minus j, and we take the integral of fj with respect to mu minus the integral of fj with respect to mu, and we put the absolute value here. I will always use the notation f mu is the integral over x f value. Then we discussed a lot about large deviations. So let us consider a sequence random sequence in x, which is px. Then we introduce the concept of rate function. So if we have function I acting from x to r plus bar, which means positive numbers plus infinity, then definition say that I is a rate function. Very often I will use the abbreviation RF if I is lower semi-continuous.
That's all.
That's all, yeah. And now, well, let me just recall the definition of lower semi-continuity. With lower semi-continuous, by definition, it means that for any C, the set of points where I is smaller than C is closed. So in our case, it will be compact because our space is compacted. Our main definition of
Mnemonic him. So this is so low semi-continuous, it can jump in the one direction. How to remember which way? Everybody should remember that the lowest continuous function achieve maximum on the call. Maximum. Minimum on the call. Therefore, we immediately see that we can jump on the down. This is a way to memorize. Otherwise, it's really complicated. You should every time open Wikipedia. But it's like,
Yeah. Now, the main definition was the following. We say that mu n satisfies the large deviation principle with a rate function I if you have the following. Let's use the second version of the definition. For any f close the upper limit of 1 over n with the mu n f is more than minus I of f, and I of f is just the infimum of f, infimum of I over f. So obviously this is the same as saying the following. For any epsilon, there is n epsilon such that for any n greater than n epsilon, this probability mu n is in f is smaller than exponential minus n and ef minus epsilon. So this is the first part. And the second part is for any g open, the lower limit as n goes to infinity of 1 over n logarithm probability mu n is in g is greater than minus I of g. Let's know that this second estimate can be empty if this I of g is equal to plus infinity. It may ask. If at any point of g I is equal to plus infinity, this I of g is equal to plus infinity, and you have minus infinity here. So any lower limit will be greater. And as in the case of closed set, we can reformulate it in the form of inequality. For any epsilon, there is n epsilon such that for any n greater than n epsilon, of course, this n epsilon depends also on f here and on g here. The probability that mu n is in g is smaller than exponential minus n I of g plus epsilon. Okay, so this is the definition of large deviation principle for a sequence of for any sequence, that we should think always about the sequence of random measures on the space X.
Always large deviation principle is understood for sequences of measures. So
no, because it's a sequence of random variables. You can reformulate this as a property of measures. Yeah, I mean because this is a statement about the law of mu n. What is written here does not depend on the probability space. It does not depend on concrete realization of this mu n. It depends only on the law of mu n.
yes.
So you can say that I consider the law of mu n, but the law of mu n will be what? It will be a measure on the space of measures.
Okay.
So you can formulate it as a result about the space of measures on the space of measures.
Okay, so in principle, this is, so to say, less elementary statement about random variables, but it is more invaluable way to formulate because the laws of these random variables and then the measures.
Yeah. Okay, so this was the main definition. Maybe I should close the window because there is some noise. Shall I close or it's okay? Yeah, and then I calculated, I proved some results, which will be useful today. The first result was the contraction principle. So I announced a free theorem. Theorem 1, contraction principle. It says that I will formulate it in a short way. So it says that if mu n satisfies the LDP with I, and I have a function phi from x to y, where y is another Polish compact metric space, is continuous, then this implies that phi of mu n, there is another sequence in the space y, satisfies LDP with a rate function which can be written explicitly, j of y is equal to I of phi minus 1 of y.
Armen, then I just quasi-repeat my question. Why you assume that this x cross is a space of matches?
Yeah, this is what I'm interested in today.
Okay, but just because you see even now y is not a space of matches.
Yeah, in this case it is not space of measures.
Right.
In the other term it is not, but the consequence it is, because I want to connect now with the Legendre transform or something. Right?
Right.
I want to connect with the pressure and so on. In that case, I need that to be space of measures.
Why?
Yeah, because of the structure, it's like that. I mean,
By just
yeah, you can do also that. Yes, but
yes.
That's what
This is simply your habit. So this is simply how you used to treat.
No, in the case of
Kiefer theorem,
class deviation more often it's for measures.
For random variables in space of measures.
Even more, in more general framework, it's class deviation is the description of the behavior of a measure.
Random measures.
no, measures. For measures.
Random variable generates measure, one measure.
Yeah. Oh, in fact, yeah, maybe I should specify one thing. We are writing a book with some people about large deviations and some other stuff. And then we started to write large deviations from this unique point of view as I'm going to describe in the space of measures, even if it is measures on the space of measures. Which means that in fact these are random variables and we consider their logs. Well, after writing it, we understood that we should have separated the two cases because some things are very natural. Some results are very natural in the case of measures. Those are the others are natural in the case of random variables.
Okay, fine.
But it is possible to unify the two theories, but in some cases we separate them for that more problem.
You mean that it's getting more intuitive in a sense?
Yes, in a sense, well, in some cases, in the case of Kiefer theorem, it is more intuitive to deal with the space of with random variables rather than measures. Now, the second result is called Varadana lemma.
Yes, because when people start to talk about stochastic differential equation and just speak about measures only, it's relative. For example. So indeed, it happens sometimes.
Varadana lemma says that if mu n satisfies LDP with a rate function I, and you have a continuous function from x to r, continuous from x to r, then you have the following. If you calculate the limit as n goes to infinity of 1 over n logarithm mean value exponential and f of mu n, then this can be calculated explicitly in terms of f and the rate function. So this is the supremum when x is in x, f of x minus I of x. And we have an important corollary from this result. Because in a particular case, when f is given f on a measure mu, is just the mean value of some function v with respect to mu. Right? For instance, in this case, it is important that you have measures on the space of measures. And those are present.
Just dual space, right?
Yeah, but then you need to say that your compact space is indeed embedded in some vector space. That's another option.
Ah,
Yeah, so it's a bit. Yeah, of course, you can say that it is embedded in the system. So let's assume that f of mu is given like this, and v is a continuous function of x. Then obviously v is a continuous function on the space of measures. So this condition is satisfied. And then this formula implies that the following limit, which has a name. So I assume that mu a satisfies LDP with the rate function I. Then I can rewrite this expression, this relation as follows. The conclusion that there is q of b, the limit of the following expression, limit n goes to infinity, 1 over n logarithm mean value exponential n, and here I have b integrated with respect to mu n. And this can be calculated as the supremum. Now I change the notation, I use mu rather than x, because now this is true for any x, for any compact matrix I said. Now I'm talking about the case when you have your x is the space of measures, then you have v mu minus I of mu. And here, the supremum is taken over all x, therefore it's taken over all v in C of x. And in particular, if your rate function I happens to be called x, then you can reconstruct the rate function I from the pressure. I of mu is equal to and taking it over x, and this is P of x. I of mu is equal to supremum when v is Cx, v mu minus P of mu. Yes, so a simple consequence of Varadan lemma is that if you have measures on the space Px, if you have random variables with range in Px, then the pressure exists and it is given by this formula. So this is the Legendre transform of I. We assume that I is equal to plus infinity on the complement of Px, right? Px is embedded. This Px is embedded in the space of all signed measures. So usually, Legendre transform is defined on a vector space, not on a compact space. But you consider this as a subset of Mx, assuming that I mu is equal to plus infinity when mu is not in Px. Then when you take the supremum or all mu in Mx, it is the same as the supremum or all mu in Px, because in this case, it is just minus infinity. And then, if I is convex, the Legendre transform is revolution even in the infinite dimensional case. We can reconstruct I of mu as the Legendre transform of the pressure Q. And we had a third result. We had a third result, theorem 3. I will formulate the corollary of theorem 3 than the theorem 3. Is compactness, large deviation compactness. And says the following. Let's assume that you have a sequence of random measures. Sequence of, well, it is for the general case, but let's assume that these are random measures. Just to get used what is coming. Random measures on X. And let I be a rate function. Such that the following property holds. I call it property P. If nk is equals nk going to plus infinity is such that if nk and a rate function j from are such that you have large deviations up and low bound for this subsequence. The limit as k goes to infinity 1 over nk logarithm probability mu nk belongs to gamma is equal to minus I of gamma, j of gamma, sorry. And I put here dot to say that this equality is in fact a pair of inequalities. The first of them says that if gamma is closed, then the upper limit is more than this minus j of f, j of gamma, and if gamma is open, then lower limit is greater than minus j of gamma. So this is true for any gamma. So if nk is a sequence going to plus infinity and j is a rate function such that this is true, then necessarily this j is equal to this rate function I. So this is our hypothesis in this theorem. So if this is true, then mu n satisfies the LDP with this rate function I. This is all what we did last time. So I proved theorem 1. Then we discussed the proof of Feyerabend lemma and the compactness result in the simplest case, then this space X, when you have X, no, not this space, but this space X graphic, this space X graphic is just a finite set. Not that when this space is finite set, P of X will be R to dimension B, then D is the number of elements in X. So this will be again something limited. Anyway, so this is what we did yesterday. And now we want to discuss the Kiefer theorem. So let's indeed consider an example. So from now on, I assume that this un is always in the space Px. Let's consider an example when x, the right once again, Px, and x is a finite set. So nu n, what is nu n in this case? Well, what is the measure in this case? When mu is in Px, then I can identify mu with mu1, mu n, which will be an element in Rn.
So we have a question on this. The question is why the call compartments?
Why, sorry, what?
Why it is called compartments?
Yes.
Why is for compactness? Well, why do we mean by compactness? Usually, we say that a set is compact if for any sequence in that set, at least in the case of metric spaces, for any sequence in that space, there is a converging subsequence. Of course, here it is not about converging subsequence, it is something different. We are interested in some property which can be interpreted as a limit of something, right? We have a lot of limits here which are described by some function J. So we can interpret this convergence as the convergence of this space of measures to this limit. Now the property says that, well, not this property, this was the corollary. The initial property said that for any sequence of measures on the space X, or random variables in the space X, there is a convergence, there's a subsequence which satisfies the large deviation principle. So in that sense, it is a kind of convergence to some limiting function.
Armen, was right last time the statement of general?
What was,
Last time the statement of compartments in general.
yeah, because this was the corollary. This wasn't the compactness. This was the corollary.
Okay, because this is intuitive for me, but not the theorem. Yes.
Theorem says that
This is really nature for me, but the theorem. No. And this is Pухальский, this is essentially.
this is the point of view of Pухальский, and I think the theorem which I formulated is indeed the result of Pухальский. I mean, the result by itself is not that maybe it was done earlier, but I mean, it was the first to suggest how we can use just proving uniqueness of the right function implies LVP. So this was, I think, the main idea, and surprisingly, the paper is published in obscure collection proceedings of a conference somewhere.
No, he's not a practical person, but he's.
Anyway, so
and first means the best, one of the best papers we say on probability is published in journal, Czech journal, which never in Russian, which never was translated in English. Yes, yes. So everybody could easily say that no, I do not read it because it is in Russian.
okay, so let's go back to if it is okay, then we first. Okay, thanks. Okay, so then let's consider this example. Any measure can be identified with a vector in Rn, but it's not arbitrary vector. It should have a positive element, and the sum should be equal to 1. So I can identify Px with a simplex in delta n, which will be the set of points, say P1, Pn in Rn, such that Pj is positive for any j, and the sum is equal to 1. The same in the space of continuous functions. Continuous function, if we have a function f which is continuous, then I can construct f of 1, f of n. This will be arbitrary element in Rn. Therefore, the Cx can be identified with Rn. And what about the duality between f and mu? If I want to integrate f with respect to mu, what I need to do, I need to take the sum j from 1 to n, f of j, mu of j. So in other words, this is just the inner product f nu in Rn. And so in this particular case, when you are studying measures on a finite set, the concept of large deviation, of course, makes sense. But in contrast to really prevent, in contrast to the case when this x is finite, here the result is far from being trivial. So there is a general result which shows that, which gives sufficient conditions for the validity of large deviation theorem, large deviation principle, and gives an explicit expression for the right function. Okay, so this just to justify what I'm going to say now. Even if I say that now from now on, I assume that we are working in the space of measures. In the case of I'm obtaining only sequences with ranging px, I will consider just for this result the space a random variable with ranging Rn, or I will probably replace n by v. Now let us consider a sequence be a random sequence in Rd. Well, if you don't like Rd, you can assume that in a random sequence in delta d, and this will be the case. This will enter into the framework studied there. Now, the following theorem is due to Gardner and Ellis. I will formulate this theorem. We'll discuss the conditions and the conclusion, but I won't prove this because this is in any book on large deviations. There's often almost any book in large deviations, you will get this theorem. For instance, Ben Hollander or propose to me or anything else. Suppose that for any alpha in Rd, there is a finite limit Q of alpha of the following expression, and I will write exactly what is written here. Right. 1 over n logarithm mean value exponential n alpha sine. I will write here a little index t to emphasize that this is an inner product in D. This is exactly the expression written there. Now the duality is given is just the duality in Rd. Right? So here we have the duality between Cx and Mx. Now we are in the finite dimensional case. We have a duality in Rd. So this expression can be called pressure is exactly the one which comes from Varadan length. If you hope to have large deviations, this limit has to exist. So Gardner-Ellis says, okay, so let's suppose that for any alpha, there is a finite limit. When I say finite limit, I really mean that it is in R. And we have a function from Rd to R is differentiable everywhere. Then the second part of the result says that if this function I, which governs the right deviation principle for the sequence, happens to be convex, then it must be given by the Legendre transform of the pressure. Now we have this function Q of alpha. So then psi n satisfies LBP with the right function, which is given by exactly the Legendre transform of Q of alpha, in particular this convex. I of R is equal to supremum when alpha is in RD. R alpha D minus Q of alpha. This is the Gardner-Ellis theory.
When was it?
Sorry?
When was it proved?
Well, it
Well,
must be,
40 years ago, yeah.
yeah, it must be 70s, 80s, and 80s. Probably. I didn't check that.
That was a PhD student.
Yes.
Yes, and he proved this and he was
Ah.
Who? Gardner.
Gardner.
Yeah,
He was still in the pool.
I don't remember. He's from Eastern Germany, so of course he.
Okay, so, well, this result can be applied to that particular case, right? So if R of X is finite, then you just need to check this condition. And we can find a sufficient condition for differentiability. For instance, you can consider. I wanted to say you can consider finite state partial chain, but you cannot, right? Because yes, you can. Yeah, you can consider finite state partial chain.
May I make a small comment?
Sure.
In fact, this Gardner theorem, it's only part of it. The full version also discusses the case of not differentiable, not strictly complex. And in this case, there are only estimates, not full-fledged division principle, but some estimates, which might be also very used.
Yeah.
But that was before the theory of large deviation, so it was properly developed, right?
Yeah, that I don't know. Well, in fact, long deviation, as we discussed here, consists of two parts, right? Upper bound for closed set and lower bound for open sets. Right. The very existence of this limit implies the upper bound for closed sets.
Yes.
When you have initial differentiability, you have also lower bounds. When you don't, you cannot take there the infimum over G, but you need to take the infimum over G intersected with the what is called the exposed set of this function Q. But that is not needed now. It's more subtle result about lower bound. So upper bound roughly this upper bound.
Yeah.
Okay, so how do you deal with problems in infinite dimension? So basically, you need to approximate by finite dimensional problem.
Yes.
So let's try to approximate this by finite dimensional problem. And let's see how we can combine what we know already to derive a result. So let us denote by G the finite subsets of CX. Right? Just any finitely many any set of finitely many continuous functions. Now let us consider a gamma, which will be the element of G. This will be V1.
What does it mean finite? Bounded or finite?
No, just a finite subset. This is a set, right? Set of continuous functions. I pick up finitely many continuous functions. V1 VD, which will be an element of G, right? G is all sets of this form with arbitrary many but finitely many functions. Now let us consider phi gamma. This will be mapped from Px to Rd, where this D is exactly the number of elements in this gamma, which is given by the formula P gamma mu is equal to V1 mu VD mu. Right, so I consider a map from Px, which is my main space X graphic, to the space Rd. It takes a measure mu, the mean value of V1 with respect to mu, Vd with respect to mu. Obviously, this is a continuous function. Now, we know by the comparison result here that there is a sequence nk going to plus infinity, and there is a function I, rate function I, going from Px to R plus, such that this subsequence, okay, let me write it, such that the limit as k goes to infinity, 1 over nk, logarithm probability psi nk belongs to gamma is equal with the dot above to minus I of gamma. Right, so this is true for any gamma in Bx. Right, so we notice that at least for one subsequence, there is this relation. Now, here's a key assumption. Suppose that I will assume that for any gamma, but it is too strong as an assumption, but let's assume, to simplify things, that for any gamma in J, this sequence phi gamma nu satisfies LDP with a rate function, which I will denote by A gamma. Well, this is a key assumption. To prove that, I have this. So on one hand, I have one subsequence for each you have large deviations along a subsequence. On the other hand, I assume that for any gamma, phi gamma nu n satisfies large deviation principle with some rate function I gamma. So I gamma will be a function from R d to R plus bar. Now I apply the contraction principle to psi and k. So by the contraction principle, phi, there is my sequence, for any gamma, phi gamma nu n, nu nk, sorry, nu nk, satisfies LDP with the rate function, which can be written explicitly. This will be J gamma of phi gamma minus 1 of y. Okay, now let us look what we obtained. Phi gamma nu n, sorry, it's not J gamma. This is just I. Because I got some I, and I'm calculating the rate function, the contracted rate function. Here is the contracted rate function. This is the contracted rate function, which I'll denote by J gamma of Y. Okay, so according to the contraction principle, if I have I LDP for new n, if I have a continuous function, then the image of this sequence satisfies LDP with what I call contracted rate function. For any y, I take the full inverse image and I calculate the infinite of I on that set. Okay, so once again, this is already given, right? Because we have this theorem 3, which says that there is a subsequence for which I have the large deviation principle. I made this assumption. Suppose that by some miracle I can prove that phi gamma nu n satisfies the LDP. Here is a result which will guarantee that. So if for this contracted sequence I can apply Gardner-Ellis theorem, then I will have large deviation principle with some function I gamma, which is given by this. On the other hand, if I apply contraction to this one, sorry, there is no contraction, it is just an assumption. If there is a large deviation for the subsequence, then contraction says that the image phi gamma nu k, nu n k, satisfies large deviation with this contracted rate function, which I denoted by J gamma y. But what we get here is a subsequence of this one. What we have here is a subsequence of this one. And if this satisfies large deviation with the raised function I gamma, I can consider the same thing. For any gamma in R, let me write like this, R gamma, for any y in R gamma, I have I of phi gamma minus 1 is equal, so this is the contracted rate function, is equal to I gamma of y. Psi n k. There is no psi n k. This is un k. Okay, so there was a mystery. So let's go. Let's begin once again. So we have a sequence mu n in the space, random sequence in the space of Bezier forms, in the space Px, which is x calligraphic. I consider all finite subsets of continuous functions. And I consider a large family of continuous functions, phi gamma acting from Px to Rd. D is the number of element in gamma. Obviously, this is a continuous function from Px to Rd. Now 2 points. First one is just theorem 3. There is a subsequence such that you have large deviation principle. This is an assumption. Suppose that for any gamma in G, we can prove that this phi gamma image satisfies a large deviation principle with some rate function I gamma. The first one is guaranteed, the second one is a hypothesis. Then, applying contraction principle to this sequence, I can conclude that phi gamma nu k satisfies large deviation principle with a contracted rate function as specified there. I denote it by J gamma y, and j gamma y is given by this formula, I of phi gamma minus 1 of y. But this one is a subsequence of this one. So they must satisfy the same large deviation principle. So the corresponding rate function must be the same, which means that for any y, for any gamma in G, and for any y in R gamma, you have this equality. Now let's recall this. If for any subsequence satisfying large deviations, I can prove that the rate function is the same, then I have large deviation. So now here I said that there is a subsequence. In fact, I could have said that let's consider subsequence which satisfies this large deviation principle. So what we have here, we have that this function I, which may depend on the sequence, on a lot of sets is defined by I gamma, which is universal. So this is the key observation. I have I, which depends on the subsequence. If this is true, then this I must satisfy this relation for any gamma and for any y. This is true for any gamma and any y. Now this is a subset of X, right? This is the inverse image of gamma on X. And what is written here is the infimum. So this is the same, saying that infimum of I phi gamma of y, phi minus 1 of y, I forgot I of phi gamma minus 1 of y is equal, sorry, what I'm writing the same thing, but I should write I of mu when mu belongs to phi minus 1 of y. And this is equal to I gamma of y. Right, so I have a function depending on nk such that this is true for any gamma and for any mu or for any y. So the infimum of I on very large family of subsets does not depend on the sequence. Now, if this family of subsets is sufficiently large, then you will have uniqueness of I, and therefore large deviations. This is the key idea. For instance, let us take here for y. Let us take for y the image of the given measure in Px. This is true for any y. I have the right to consider this. Then what we get? We get that the infimum of I of phi gamma minus 1 of phi gamma mu when there is no infimum. I of phi gamma minus 1 of phi gamma mu is equal to I gamma of phi gamma mu. I just wrote this relation in the particular case when y is equal to phi gamma mu. So I have a measure here. This is my Px. I send it to R gamma. I get phi gamma mu, and I consider the inverse image. This is my y gamma, and I consider the inverse image. This is phi gamma minus 1 of y gamma. If I take large and large gammas, this will shrink to mu. Let's take let's take a sequence, this sequence. Then it's not difficult to see, it will do that this will shrink to the singleton group. And therefore, you will end up y of mu is the limit of this when this gamma gets larger and larger. This proves the uniqueness, because what is written here does not depend on NK. And according to theorem 3, if we can prove that any subsequence which satisfies the large deviation principle does it right function in the subsequence, then we have obligations. So, I managed more or less to tell you about the main idea in Kiefer's theorem. This is a really highly non-trivial observation, which was the main contribution of Kiefer. He did it in very, very complicated ways, so it took us several years to understand that this is what is done. So now I will formulate a result, which will show which condition is related to the property. Sorry, can you might see to now if I write this script, it will be 2 pages, but there will be a lot of preliminary results.
This will be in this way.
Yeah, it will be. Okay, so I will now formulate Kiefer theorem. It will be clear. Theorem. And this is the result of Kiefer of 1919. Is that length? Yeah, almost 35 years.
Was a nice student and then was similar.
When new ends, the random sequence set available in the PX such that the following 2 properties. The first one is called existence of pressure. I will write it EP, existence of pressure. For any V, there is Q of V, which was defined there. So let us write once again the limit. When n goes to infinity, 1 over n logarithm mean value exponential n V and nu n. So there is a finite limit.
With X, with X now.
X is as usual the partnership space there. So the part distance of limit, let's suppose once again that if you have one relation with that limit is. For the second condition, I will need a definition. I'm sorry, I forgot to mention it. I will need a definition. We write it here, definition. Let's recall that this Q of V can be written as this expression. And now we don't have I. So first I define I. When I we defined by that formula. I of mu is the supremum when V is Cn of Cx, V mu minus I mu. Minus Q of V. Okay, I have this function. I assume that this limit exists. So I define Q of V, I of mu by this formula. Now we have some properties of I and Q. Properties of I and Q. First of all, Q, which is a function from Cx to R, is one Lipschitz and convex. So these are soft properties. One Lipschitz just a one-line inequality. Convex is just Holder inequality. It is really soft. The second one is I is lower semi-continuous and convex. Well, again, you do the Q from I for any V in Cx.
And lost.
Yeah.
This is common to saving, so this should be for saving. What you're writing now. What is the relation of what you're writing now with this?
I should have said, let us consider measures for which this property is satisfied.
Yes.
Then let us define I. Then the following properties hold for I and Q. Then there is another property which is defined in terms of what I'm going to say now. Okay, so I will repeat it once again.
But always is a claim of Kiefer saying.
No, well, Kiefer, well, this is just simple result because no long before. Let me just finish this and I will repeat it once again. Okay, so for any V, Q of V can be reconstructed by as a Legendre transform of I. Mu is in Px. This V mu minus I of mu. So let's call, I didn't give any numbers today. So let's this be is number 1. This is number 2. Well, this is a standard result in convex analysis. It is a consequence of Hahn-Banach theorem, essentially. In this particular setting, when everything is compact, the supremum in 2 is attained, which means that for any V, there is mu such that Q of V is equal to V mu minus I mu. Well, again, you do the most natural thing to do, you just choose a minimizing sequence. Q of V is the supreme of something. What I'm saying is that this supreme is attained at some function V. To prove it, choose a minimizing sequence. Then you can find a converging subsequence, right? Because P of X is compact. These will converge, and this is lower semi-continuous. You will have the right inequality in the limit. Yeah, we can. Let me write also these two pieces, and we'll discuss all of this. Okay. Then definition. So this is relation 3. Definition. Mu is called the equilibrium state I will write ES for V. V is a function. If mu satisfies 3. Okay, so let's make a break here and let's consider what we have. So we have mu n, which is a random sequence of events. So for each n, mu is a random variable taking values in the space of S. I assume that for any continuous function v, this limit exists in this time. And this is what Varadana said. If you have one relation, the necessary this limit exists. Now, this limit satisfies some properties. It is one Lipschitz and convex. I know for the if large negation holds and I is convex, then necessarily should be given by the Legendre transform of Q. So let's define that function. I mu is v mu minus 2v, and I take the supreme over all v. In contrast to Q, this function may be infinite. So it takes values in R plus bar. Now what we can say about I is logically continuous because it is the supreme of affine functions. Right? It is affine with respect to mu, and we take supreme of affine functions. It's logically continuous. It's not difficult to show. And it is convex again by some elementary considerations. Then a bit, but not a bit, but far less obvious result is that the Legendre transform is an involution in the sense that this function Q can be reconstructed as the Legendre transform of I, assuming that I is equal to plus infinity on the complement of P. Okay, we have this formula. Now, a soft result, which follows from here, and the compactness of the space Px is that this supremum is attained. How you can prove it? Just choose a maximizing sequence mu n. Because X is compact, you can assume that it converges weakly to something. Then V of mu n will converge to V with respect to that something, to that limit. And here you don't have convergence because you don't have continuity, but you have also the continuity, and it turns out that it is the right sign. You will have that the limit is greater than like this expression of the limit is greater than any of these functions. Anyway, the supremum here is attained. Now, measure mu is called an equilibrium state for a function v if it saturates this supremum. So, in other words, if it satisfies this relation. Usually, you have that QV is smaller than this, but for some measures, it is equal. Sorry, yeah. 1 second. QV is super. Usually, you have that QV is greater than this. But on some measures, you have equality, and those measures are called equilibrium states for V. Now, the second hypothesis, uniqueness of equilibrium state. There is a dense subspace, and it is indeed important that it is a subspace, not just a subset. There is this dense subspace V in CX such that for any V in this V-Calyx graphic, any V in this V-Calyx graphic has a unique equilibrium state. Then mu n satisfies LDP with the rate function R. So this is the Kiefer theorem. It's really easy to formulate. Let's compare it with the hypothesis in Gardner-Ellis theorem. Gardner-Ellis theorem says that the pressure exists exactly as the first hypothesis in Kiefer's theorem. The second hypothesis in Gardner-Ellis theorem is that Q should be differentiable everywhere. Differentiability of this Q would be very restrictive. But this differentiability can be reformulated in terms of uniqueness of subdifferential. And here we call subdifferential just equilibrium state. And that should be true not for any V, but for a dense sequence, dense subspace. And it is indeed important that it should not be, it suffices that it is true on a dense subspace, because in many cases, for instance, in the case of stochastic PDEs, it is not true that you have uniqueness on every functional CX. Well, it is almost 5:15.
Yes.
Maybe it's a good point to make a break, but it's not explaining this like this. So take a break.